Okay, we're going to be looking at problem number 11 and 12 on page 492 from chapter 9. These are going to be about the confidence level and confidence interval widths. I have just sketched a sampling distribution of p hat here, and I have just denoted the fact that the center of this sampling distribution is the true population proportion p, because the sampling distribution of p hat, my sample proportions, should be centered around my population proportion p. Now the first part talks about which is going to be wider, a 90% confidence level or a 95% confidence level. While 90% confidence level would basically contain the middle 90% of my data. So if I'm talking about a 90% confidence level, I'm looking for the middle 90%, which is going to be about here, is going to contain the middle 90% of my data. So that would be the 90% confidence interval. 95% confidence interval would have to contain the middle 95% of the data, so I'll do this one in red. 95% is approximately between 2 and -2, so there is a 95% confidence level. And that's what we have. So obviously to be 95% confident, you need more room for error, so that's going to be a wider interval for your 90% confidence interval. Next part of the question asks you to compare a sample size of 100 and 400, so we'll erase these recent notations. And when we compare the two sample sizes, I'll say that what we have here represents the sampling distribution of p hat with a sample size of 100, and we'll kind of sketch what would be the difference if the sample size was 400 in a different color, maybe in green here. So if the sample size is 400, what that is going to do is this standard deviation here that is denoted by this distance here is equal to the standard deviation of p hat, and the formula for that is p times 1 minus p divided by n, and taking the square root of the whole thing. Now, that standard deviation will increase as the numerator gets larger, and if you think about it, the numerator will be larger in cases where the probabilities are close to 50-50, because the maximum value of that numerator would be 0.25, which would be a 50-50 probability, because if I have a 0.5 for p and a 0. That means not p is 0.5, so my numerator is going to have the maximum value of 0.25. As it starts to get further apart, maybe like 30% and 70%, that numerator is going to get smaller in value. So you're going to have your maximum variability when it's a 50-50 probability. Now, the denominator, on the other hand, increasing the denominator will decrease the variability. So a denominator of 100 would basically simplify to a denominator of 10 with the square root, and the denominator of 400 would simplify to a denominator of 20 with the square root. So basically, whatever this variability is, instead of being, it's going to cut by half, because that denominator is going to cut in half, comparing square root of 100 to square root of 400. So instead of my distribution looking like it originally did, it's going to condense heavily. And since it's condensing heavily, it's also going to be a lot taller. I probably could use even more room to graph than what I have here, but I think what we're going to have here is a distribution that looks something like this, where it goes up, it's very peaked in the middle, and this. Now the reason this distribution is much skinnier again is because the total area under it should still equal 1, whether I'm talking about the distribution there or the distribution there. The total area under the curve should still be 1 or 100%. So the one that has less variability, less width, is going to be the one with 400, and therefore I'll have to have more height to have the same area. So the answer is that you have less variability, less width to your confidence interval with a larger sample size. Now when we go on to problem number 12, it's wanting some information about how to get critical z-values to cut off a certain percent. So we'll start with just a 95% confidence interval. So if I'm looking for the middle 95% of my distribution, once again, that's about 2 and -2. So I'm going to be within basically 2 standard deviations of the mean, but I'm going to show you what we could do to get an even more exact answer than just this. If 95% is in the middle, it's important to realize that the sum of the tails is going to be 0.05%. So 95% in the middle, that much in both tails put together. So this one tail over here is 0.025. So what I'm looking for is a critical z-score that cuts off the bottom 0.25% of your distribution. There's the formal notation you would use to denote what you're looking for. And then to get that answer, what I'm going to do is I'm going to reach for the calculator. On the calculator, I'm going to do inverse normal, so second distribution, inverse normal of 0.025, and then paste, and that gives me negative 1.96. Now from the empirical rule, I did know that I was going to be kind of close there, but from the empirical rule, I do know that my middle of my distribution should be about -2, so that's negative 1.96 is good so far. The next one wants 90% of my distribution, so I'm going to just sketch a normal curve again. And I'm looking this time to the middle 90%. So if 90% is in the middle, clearly there's going to be 10% that's on both ends put together. So that's going to be 0.05 for each end. So if there's going to be 0.05, I'm going to reach for the calculator. I'm going to do second distribution and inverse normal, and this time of 0.05 because that's my area below that lower z-score, and that's a negative 164. Usually you'll see that rounded in this case to 3 decimal places since it's about right in the middle. So that's going to be negative 1645. So that is going to be the critical z-value, plus or minus 1.645. And sometimes you will just see that written as the positive one because obviously since distributions are symmetric, you're going to have 1.645 standard deviations above and below the mean to capture the middle 90%.